Thank you very much, Chairman, for your presentation. Thank you to the organizing committee who asked me to present this work. And just some introduction to this work, because I'm talking about a multidisciplinary approach for Homeland Protection Systems. I have to say at the beginning that I'm an engineer, so I usually have a technical approach to this kind of systems. But talking with customers and funding organization, because this project that I'm presenting needs funding, of course, I learned how much this topic is multidisciplinary. And so this presentation is also a summary of my thoughts about that, which have been stimulated by real talking with people and with organization. Okay, anyway, this is my approach, of course. So if I say something wrong, you can argue about that, because there are many ways of thinking the same thing. So first of all, just an introduction to Homeland Protection System. I know that everybody knows what they are, but I can say that Homeland Protection Systems are really part of our life every day. They are part of our wealth, our society. For example, transport, the transport system, the communication system, the territory protection, all things that are very tied to our way of life. And we have to be secure in our everyday life. So it's important that we can ensure this kind of wealth in our life every day. I can say, unfortunately or fortunately, this kind of systems are in any case very complicated or complex systems. For example, think about communication systems. We are, of course, everybody is using very smart systems for communication every day. We use a very complicated system of transportation by car, by air, and so on. We have a very complicated system for distributing the energy. And the result of this is that we have to face with complex systems. And a complex system is made of a lot of individual elements. But the nature of the whole system is that the interconnection between these elements is quite complicated. So the result of this is that it's very difficult to study these systems only by studying the subsystems, the individual elements of the system. We need to study mainly the interconnections. This is the point. And in order to do that, we need a multidisciplinary approach. Another point that for me is very important that in order to study these systems, we need a powerful analysis tool. And this tool cannot be a general tool. This has to be done for each of these systems. This comes from personal experience. So it's true that when designing this tool, we have to follow some general rules. But we cannot use one tool for each system, because every system is different from another. When dealing about the design of this tool, we have to take in mind that this tool have to manage the complexity of the whole system. So it has to take into account all the cause-effect links which are inside the system. I made an example in this slide that is taken from real life. And this comes from an example taken from the emergency operation after the Hurricane Katrina. This, of course, is the emergency system are another example of Homeland Protection Systems. There was a clear mistake which was made during these operations, which was done basically for a reason of that the operation were not prepared carefully. The result of stopping all vehicles entering in the New Orleans city after the hurricane caused the inoperativity of the emergency centers, because, of course, there was no electricity. It was necessary to recharge these operation centers via vehicles transporting oil. These vehicles were stopped, and so these operation centers became inoperative. This is an example how it's important in a complex system to take into account of all things cause-effect and manage all these links together without forgetting anything. The analysis tool, what is the role of this tool? This tool has to be used not only to design and manage the system, but also to understand the economic impact and the social impact of the system. So this tool is omnicomprehensive of all the impacts that the system has on the scenario. And another important function of this tool is to manage situations that can happen. These situations include malfunctions. Every system, even the perfect system, can have malfunctions. Natural threats, for example, we have seen before hurricanes, maybe fires or earthquakes, whatever. And maybe more threatening is the human threats. An example is terrorism, but there are also other examples different. For example, internet, hackers, things like that. I could say that combating human threats is the most challenging work for these systems. And the reason is that the human threats use the same technology that we use to build the system. Think about, for example, the communication. Even if we use very sophisticated technology to build telecommunication systems, the same technology is used by hackers to make these systems inoperable. One point, very important point, that for me is a crucial one, is that for the human threats, we have to adopt some kind of military doctrine, which is that of not intervening after a damage has been produced in the system, but acting before. So the issue is that we have to prevent the potential enemy to make some damage and not to act after the damage has been produced. In order to do that, for example, in the case of terrorism, and this also justifies the reasoning about the multidisciplinary aspect of these systems, we have to consider, first of all, the logic of terrorists. So to understand the reasons in order to mitigate, at least mitigate, the causes of terrorism before combating with the technological equipment. There are also some tools that already has been developed in this area. This is a list of tools existing for calculating the risk, for example, to understand or to forecast which type of infrastructure is more subject to human threats. Every tool is dedicated to some particular scenario. So, for example, there is the maritime scenario, there is the transport scenario, and so on. In general, the infrastructures, which are the core part of our life, communication, transport, but also education, universities, and so on, they are the goal of human threats. Because when damaging one of these infrastructure, someone can damage all the others, because these infrastructure are connected with each other in a very tight way. For example, it's clear that terrorism is one of the main actors for this kind of damage. But another one is the cyberspace. Also because an action on the cyberspace could be also a preliminary action to damage physically something else. We can read on the newspapers every day. For example, I read also in the Today newspaper about some damage that was recently done to the US communication infrastructure by hackers. But we can have these examples in every country every day. The vulnerability of critical infrastructure, for example, the electrical grid, is quite important. There is a famous example, that of the August 14, 2003 blackout in US and Canada, which was due to very trivial problem, and that is the damage of some electrical lines. This damage propagated very fast to all other infrastructures, and at the end of only one day, it produced a total damage of about $10 billion. Going ahead and discussing the case of urban critical infrastructures, which is the core part of the topic where I am studying these systems. The problem is when dealing with this kind of scenario, the first point is that we have to build a very huge network of heterogeneous sensors. This means that in a city, like a large city like Rome, for example, we have to dispose something like 1 million of sensors dispersed in the city. Maybe that I will have the time to explain why this. There are two possible options. If you want to remain with the traditional process, that is the human-based process, we should be able to elaborate a huge amount of data, because I said before, we need some million of sensors dispersed in the city. So we need a huge amount of people to do that, and this is, of course, impossible. Which is the solution? The solution is that we have to reduce the rate of the data, and in general to reduce the amount of data that we have to deal with, and we have to do that automatically without human intervention, and then put the human intervention at a higher level. And in fact, this is the second option, the automated process. So we have to take this amount of data, big data, which are produced by the different sensors sparsed in the area that we want to control. We have to take the information that is necessary, because most of these data are not useful, and we have to convey this data to a single center where the human presence is important, because the final decision is not taken by the machine, it's taken by the human being. And this is the result that I will present very briefly because of restricted time. That is URBEM. URBEM is a prototype that we built. It's not the control of an entire city, because this kind of system will require a very big investment. This is the control of a limited area, and instead of disposing a million of sensors, the number of sensors is about 100. Well, I will go very fast in this description, because maybe it's too much technical, but just to understand that when dealing with this kind of heterogeneous sensor system, we need to involve a lot of technologies. For example, data fusion. Data fusion between different sensors is quite a particular technique to be carried out. These are the results of some experiments that we did with this network, and in particular putting together electromagnetic sensors and optical sensors. We came to the conclusion, these are some graphics that we extracted from our experiments. These graphics demonstrate that the connection between different sensors is not only useful to cover a wide area, because of course when we cover a wide area we need many sensors, but putting different sensors together at work means to improve the performance of our tracking. Okay. And these are just the results. When you look at the picture, you have to consider that the best performance is when the graphic is higher. So we demonstrate that it's useful to use not only one kind of sensor, but different kind of sensors. Another point, quite important, is that when using develop a system which relies on a wider range of the electromagnetic sensors and better precision of the optical sensor. And so use the electromagnetic sensor as a queuing of the optical sensor. And this graphic at the end demonstrates that in complex scenarios, we can improve further the performance of the system with putting more sensors. Okay, this is a summary of the capability of our URBEM system. I said before, it's not a complete system, it's only a prototype, but it demonstrates that it's possible to implement this kind of systems. Okay, there are open issues, of course, in this kind of solution that I am going to propose. First of all, I said before that maybe that we have to give to the human being only a part of the recognition in the detection of a possible threat. As a matter of fact, there is another operation which is preliminary to the monitoring and control, which is the intelligence. So the system has to be in some way prepared to discover the possible threats. And this comes from a work which is the intelligence, which cannot be made by machine. it has to be made only by human beings. So the intelligence is quite important to forecast the possible presence of which threats, when the threats can happen, and so on. And there are some questions relative to the problem, automated versus human monitoring. I can say that these questions also come from the field. So dealing with customers, dealing with funding organization, I learned that, first of all, first point, there is some skepticism about the fact that an automated system can substitute a human being in such a critical function. Second, when promoting automation instead of people working, there could be a problem of favoring unemployment. Third one, when disposing a very huge amount of sensors in a city, this means that when I take my car and go out from my home and go to some place, I am controlled in all my movements. This could be an attack to the privacy of the people. Fourth point, the cost. Is it cost effective or not? Because if not, of course, it's not useful. So I tried to answer these 4 questions, but I don't know if I answered completely. Anyway, I would like to present very shortly these answers. So the first answer, the role of automation in modern life. I reported some statistics regarding plane crashes. These statistics come from National Safety Council, and they say that the 57% of the airplane crashes are caused by human errors. It seems that nearly 0% is caused by electronics, because the main part of the crashes due to some failure of the system are related to mechanical problems. Maybe it's too optimistic to say this, but anyway, the conclusion for me is that the human being cannot be excluded by critical activities like, for example, piloting an aircraft. And in fact, up to now, we don't have, fortunately, but we will have maybe in the future, airplanes driven only by machines. But even if for the most part of the trip is the machine which is driving. So it's not possible to exclude completely the human being from these critical activities, but it's better to put the human being at top level, not to make some trivial work, but putting at maximum level. Regarding the problem of the job creation or destruction, this is another critical problem because, for example, I had this problem when proposing this system to some organizations like the European Union, because they are very, very keen about social problems also because in Europe, not only in Europe, but mainly in Europe, unemployment now is very high. I went to the conclusion that, and maybe that many other scientists also can agree on this conclusion, that automation doesn't stop employment of people, at least in the long term. Automation is that it is required more skill from people. So jobs with very low level of skill are killed, of course, but, for example, innovation require a high level of skill. So the problem is not too much to be afraid of the fact that jobs are cancelled, but to work in order to improve education and to foster the creation of better minds throughout the world. This is maybe is not only my way of thinking, is also a lot of people who think the same. Regarding the privacy, there is no doubt that if we want more security, we need to give up some privacy. The two things are completely connected together. So the main problem here is not to prevent the creation of such systems, but to make all the actions necessary in order that these sensible data, which are data relative to the private life of each person, stay in the right hands. And the final problem is the problem of cost. I will summarize very briefly this point, because I think that I'm nearly at the conclusion of my time, and also because I will present the result in a very detailed way in another paper that I will present on Wednesday. So here the problem is how much this system could be cost effective with respect to a traditional system based on human monitoring. In order to do this comparison, I took into account some metrics, and in order to avoid to specify the cost in terms of currencies, for example, euros on dollars and so on, I tried to define a new unit which is not so much tied to the currency. Is the cost unit, is a general matrix which associates the cost of for example, a sensor, and specified how much of this unit I have to use for the different operations of the system. Okay, this exercise was applied to a case study, which is an area protected of 20,000 square meters. The experiment was done taking the data of the Sapienza University of Rome, but it's only an example because they were working with us in doing this experiment. I can say that we are working in a scenario where there is a number of 500 or 1,000 people. So we designed the system just to dimension the system and took into account the implementation costs, which means the cost of the hardware and software to do the work, the maintenance, malfunctions, people working, everything. The false alarm management, because one point is quite important here, is that due to the fact that the automated system works 24 hours a day and and with a lot of sensors working together, the number of false alarms, so the number of situations where the system discovers some threats which is not real, is higher than in traditional systems. And we have to manage this point. So this higher false alarm management results in higher cost. And at the end, we also took into account the attack damage cost, which is the cost which is related to the fact that the system has, in any case, has a probability of being attacked, because no system has a zero probability of being attacked. There is still some probability, very low. For example, we estimated that for the automated system, we can have a successful attack of 1% in 1 year. That is one attack every 100 years. And we also estimated the damage consequent to this attack. Okay, the results are the following. There is a subtotal and a total. So the subtotal says that if we don't consider the cost of the damage subsequent to attacks, our system is more effective than a traditional system by a ratio 2:1. So during the time that we use the system, typically 5 years, 10 years, we spent half money than a traditional system. Okay, this could be a good reason to use these systems. Maybe that one can say, okay, but I have to invest at the beginning, so 2:1 can be not too much. Okay, just finished. But the most important point is that if we take into account also the damage subsequent to a real attack, this ratio comes to 10:1. That is much more cost effective than the previous number. And so we have to think about. So, as I said before, it's impossible that an attack cannot happen. Probability 0 doesn't exist. The cost is 10:1 with respect to the traditional system. And these are the conclusions for the cost issue. I can repeat the conclusion is that by using an automated system, we cannot be sure 100% that we can defend the infrastructure in any case, but we reduce strongly the probability of the attack. In addition, relating to the cost problem, we have a cost effectiveness for the automated system, which is 10 to 1, the one by using a traditional system. So it's a very interesting point to consider when deciding if using this kind of system or not. Okay, this is the conclusion of my talk. As every system, as every discussion, the cost is the most important, maybe in many cases, considering also the cost here means also the cost including possible loss of life, because this is included here. It's not only things, it's also the human life that is to be secured. Okay?